Hello friends, this is the second tutorial on using Python for statistical and econometrical calculations, and today we will look how to estimate cumulative distribution function and quantiles for different probability distributions. So let's start with the creation of a new Jupyter notebook. Let's call this tutorial 2. And for this tutorial, we would need basically only one library, no, two libraries. So we need to import numpy as np, and we want to import from scipy the library stats. So that's the first. We run. And then, in order to demonstrate the calculations needed, we will go through the examples used in lecture number 3 of mathematical statistics. So the first example was here. We wanted to calculate the probability that the sample average will not exceed, will not be less than 0.4 given the following parameters. So first, let's write example 1. And this is something new for you. Whenever you write something after this hash sign, this is treated by Python as just a comment. So it is not executable part of the code. This is just a comment. It may help you to understand the logic of the code. It may help you to put some necessary comments. And this is usually, this is the nice way of writing the code whenever you provide some short comments if you give your code to somebody else, so that another person may understand clearly what happens in your code. So we provide this comment, and then we define the variables. So we know that mu is 0.5. We know that sigma squared, so let's call this sigma 2, is 0.3. We know that the sample size n is 9. So here we just define the variables in the way that must be familiar to you from the first exercise session, from the first tutorial, sorry. So next we calculate this fraction, right? So the fraction, let's call this z, small z, and this is what, no, wait, one additional thing that I want to define is x. So the small x is 0.4, another thing that is needed. And now I define z, which is, sorry, I forgot to put equal sign here, which is mu minus x, sorry, x minus mu, x minus mu, divided by, now here we have a square root, and you know that the square root might be used with the help of numpy library, so it's mp sqrt. In the first tutorial we used math library in order to take a square root, so in this tutorial we can use numpy. Those two are equivalent. So the square root of what? Of sigma squared divided by n, which is sigma 2 divided by n. Okay, so let's try that everything works. I ran this code, and then separately in the new window I can call for z. So z is minus 0.5477, which is here. Perfect. So now probability. How to evaluate this probability that the standard normal distribution variable is less than the following thing. So in the lecture slides you might have seen this function stats.norm.cdf. So this is for your reference, and you may find this function in the video. So now I define probability, which equals to what? Stats dot norm. So first part of this code stat means that I refer to the library stats loaded in the first step here. Then from the library stats, I take the normally distributed random variable. So there is a package of everything that is related to the normal distributed. And from this package, I take the particular function, which is CDF. And whenever you have a standard normal distribution, so let me provide here a comment. For a standard normal distribution, the only variable you must specify is small z. So here I put the small z, and then in order to see the result, I can write down p here. So let's see. So the probability is 0.29, which is exactly the result that we have obtained in example number 1 here. So that's the way how you must be able to evaluate CDF. So let me put it here, example 1, CDF of a standard normal distribution. And another comment is the probability that large z is less than small z. Now this is more or less concise. So example number 2 is related to the quantile. So if you remember, in example number 3 in the lecture, we calculated a quantile, which was here. I wanted to find such a value b and minus b that gives me probability of 5%. Okay. So let's try doing this. In this case, I want to do the following. So example 2, quantile of a standard normal distribution. And in this case, it's gonna be p z is less than zq, let's say, and this must be equal to q. Okay, so first we need to define the probability. Let's call it q, and this is 0.05. Now, knowing this probability 0.05, I can easily calculate what is my zq, which is again library stats, the toolbox of functions connected to the normal distribution, and then ppf. And here I need to provide the value of a quantile 0.05. So let's see what is the result. ZQ minus 1.64 and approximately 5. Exactly what we had here. So let's see. If you remember from the lecture number 3, 95% quantile is just B. So let's compare this. If instead of Q, I specify 95% instead of 5%. So let's see what is ZQ. Exactly the same value, but with plus positive value. So this is how you can work with finding values of CDF or quantiles for a standard normal distribution. The same logic appears when you work with some other distribution. So let's move to the chi-square distribution and example number 4 from the lecture. We wanted to calculate this probability that some variable, so chi-squared statistic doesn't exceed 18. So let's first of all, example 3, CDF of chi-square distribution. So let's first define all these variables. So we know that sigma squared is 0.3, and we wanted s squared to be greater than 0.6. So let's call this s2, which is 0.6. Nice. So now we define the chi-squared. So let's call this chi-skew, which is, so yes, sorry, we need to know what is n. N is 10 cars, and we need to define the number of degrees of freedom, which is n minus 1, always, right? So numbers of degrees of freedom is n minus 1. So now what is the chi-squared? This is the number of degrees of freedom multiplied by s squared here, 10 minus 1 multiplied by 0.6 and divided by sigma squared. Okay, so let's check that everything is correct. Right, squared, 18. Exactly what we have here. Nice, everything works. Now we want to calculate this probability. So how we can do this? Again, we can write P equals stats. And look, now you can apply the same logic, but instead of norm, you need to use chi-square distribution. Remember from the lecture that we used this function. Where was it? Yeah, here, chi2.cdf. So I write it like this, chi2.cdf, and then I put here the value of 18, and then comma and degrees of freedom. And let's see, what is P? P is 0.965 or 48. Exactly what we have here. Perfect. If you want to calculate the reverse, you can write 1 minus P, and then you will get this 0.035. So example number 4 is quantile of a chi-square distribution. And so we calculated this quantile here. So we wanted to find lower and upper quantile such that the probability that chi-square statistic is bounded between them is 90%. So we wanted to find 5% quantile and 95% quantile. So first of all, we need to define this Q1, which is 0.05, Q2, which is 0.95. Okay, that's the first step. The second step, ZQ1, or chi-squared. Okay, this is not Z anymore, it's chi-squared. So chi-squared 1 equals to stats dot chi-squared dot ppf. Then you take Q1, and then you have degrees of freedom. So you don't need to specify degrees of freedom in this window because initially you specified these degrees of freedom here. So it will borrow TF variable from the previous window. That's totally fine. But don't forget that whenever you want to redefine the number of degrees of freedom, you need to rerun this code first and then this code. So maybe it is safer to define degrees of freedom once again here above. So now this is chi-squared 1, chi-squared 2 is stats, chi2, ppf, q2, and df. Okay, run this, and then below we can check what is chi-squared 1, 3, 3, 2, 5. Let's check exactly what we have here. And chi-squared 2 is 16,919. Exactly what we have here. Well, one additional useful thing if you want to see the outcomes. So look, if you want, for example, to put this chi-squared 1 and chi-squared 2 together here, it will not show you the result, unfortunately. It will do the following. So chi-squared 1, chi-squared 2. So unfortunately, it will show you only the last result. There is a nice function called print. So we can use it. Print chi-squared 1, and then print chi-squared 2, and then it will print both. You see that both will appear. This is the simplest possible way to see the outcome from your code, the outcome that you want. If you want to see, for example, number of degrees of freedom, you also can write print df, and you will have the number of degrees of freedom. So whatever you want to see, to make visible, you can raise the value of this variable with the help of a function print. Later, we will also go through some more advanced ways how you can form and shape the output of your code. But at this moment, probably print function will be the best possible way. So we can also use this print here. We can also use this print here. And here. Okay. Now everywhere you will see this output in the form of a variable. So next example related to the student's distribution, and well, it was the calculation of probability that the standard that the student or t statistic will be less than 0. Minus 0.5477. So example 5, CDF of a student distribution. So I can borrow the part of this code from above because some part was similar, and then I can change several things here. So mu is given the same. Instead of sigma squared, I have s squared. Okay, n is, I guess, it's the same, 9, and x is also the same. So now instead of z, I define this as t because it's t statistic, and instead of sigma squared, I need to change here s to. Okay, nice. Now, if I want to calculate this probability, first of all, I need to add somewhere here the number of degrees of freedom, n minus 1 here. And now probability equals to stats t CDF. Now I put here this value calculated above and the number of degrees of freedom. Print 0.299 or approximately 0.3, exactly as we had here. If you want to see what is the value of t, you can additionally put it here, minus 0.5477. Here. Perfect. And example number 6, quantile of a student distribution. Well, we wanted to calculate 0.025 or 2.5% quantile of a t distribution with 19 degrees of freedom. Therefore, I need to define q, which is 0.025. I need to define degrees of freedom. n is 20. Degrees of freedom is n minus 1. And then q, tq, let's say the value of t such that it's 2.5% quantile equals to stats. Then you can guess that we are taking the t distribution and then ppf, the same function related to the quantiles. Well, first argument of this function is q, the percent of this quantile, and the second is df. Print tq minus 2093. Let's compare this with our result. Exactly here, minus 2.093. And the last sampling distribution we used was F distribution. And for F distribution, the logic of your steps is exactly the same. If you want to calculate CDF of an F distribution, you do the following. So first of all, you want to define N1. Let's say it's 6. You want to define N2. Let's say it's 10. You want to define the number of degrees of freedom 1, which is N1 minus 1, and df2, which is N2 minus 1. Now you want to define some value of F, let's say, well, so let's say we want to see what is the probability that F statistic is less than 3 here. So small f is 3, and then probability equals to what? Stats f CDF. Then I take f value, then I take df1, then I take df2. Then I print my probability, and the result is 0.90, almost 8. The probability that f value is 6 numerator and well, with 5 numerator and 9 denominator degrees of freedom, probability that this f statistic will be less than or equal to 3 is 0, almost 93%. And the last example, example 8, quantile of an F distribution. It was here. We wanted to find the 95% quantile. So first of all, I need to take all this data about the observations and degrees of freedom. Then I identify what must be the quantile, 95%, and then FQ is going to be equal stats F, PPF, Q, DF1, DF2. Is FQ, and the result is 3.482, sorry, which is here, this number. So please try doing this yourself. Try to get the same results with your coding, and I hope that it will help you to deal with the calculations and computations of quantiles and probabilities that will be used throughout the whole course of mathematical statistics. See you later.